Okay, so your setup looked like this, where we had the beaker of water.
Excuse me for the interruption, but if there is a teacher who has any understanding of where the Michigan Math Prize competition test is being held right now, can you please call Judy Goodman in his office? Thank you.
Wonder if there's a frantic student that's supposed to be there. It doesn't know where to go. All right, so here you had distilled water and distilled water inside one of your cells. So that was one of the setups. The other setup, you had a 1 molar sodium chloride solution in distilled water. And then your third setup, you had a 1 molar sucrose solution in distilled water. So this is what we had. All right, so let's talk about this first one here. So let's talk about what we would expect to happen here. So what would we expect with distilled water on the inside and distilled water on the outside? Derek?
Nothing would really happen because it's equal.
Yeah, so nothing would really happen because it's equal concentration. So little to no change in there. When I say little, why might there be a little change?
The water might not be like perfectly distilled, like it could still have trace elements in it and stuff.
Yeah, absolutely, absolutely. And so, so in the inside of that dialysis tubing, maybe the company making the dialysis tubing, maybe there was, even though I had it soaking in water and so on, maybe there was trace elements of something from the production process on that, and it washed off the outside, but maybe not as well as the inside, that kind of thing. So, so that's what we would expect to happen here. And then here, what would we expect to happen? And what did we see? You should have seen happen. Did you see it gain or lose? You should have seen it gain, right? So this gained mass. And this one over here should have also gained mass. All right? So, and let's just look at our data here. And so what I'm going to do is I'm going to go around for each of the lab groups. I'm going to have you give me your data for each one of these. All right, so for the distilled water, so somebody from this lab group, we'll just go down here and we'll, so have somebody in your group have the percent change. You have yours, Julia?
1.5%.
For distilled. What about sodium chloride? 23 point what?
Wait, oh, that was sucrose. Okay.
23 point what for sucrose?
0.8.
And then
6.5.
6.5. All right, next lab group.
So the first one's distilled water.
Distilled water.
5.8%.
Sodium chloride?
4.5%.
Hi. And then sucrose?
24.3%.
0.3?
Yeah.
Okay. All right, next group, let's go. You want to do it?
Distilled water, we had 1.8%.
1.8?
And then for NaCl, we had 7.5%.
7.5?
Yeah.
And for sucrose, we had 19.5%.
Okay, group in the back, somebody?
Alright, so for H2O, there's only a 0.68%.
0.68?
Yeah.
Okay.
For NaCl, it's 5.05. And then finally, the total response over blood, 14.2%.
Okay. You guys, somebody in this group? Want to give a percent change?
For H2O, it was 1.21%. For NaCl, it was 8.5%. And for sucrose, it was 11.7%.
7.7? Okay. In the back, somebody from that group?
For distilled water, it was 0.38%.
0.38?
Yeah.
Okay.
For the NaCl, it was 9.3.
9% change.
And then 37.7.
37. Alrighty. And then
We were
You were-
with them, but,
okay.
the middle one, it was negative 4.5, like, we actually did pause.
oh, for this one?
Yeah.
Okay. All right. Huh? Okay. All right. All right. So, did I get every group? No.
For H2O, we got 1.24%.
1.24.
And then for NaCl, we got 5.13%. And then for the sucrose, we got 13.15.
Okay. Okay. So, you guys got pretty good results. So the trend we should have seen, and that's kind of what you see here, is that you have the least amount of change here. We do see that all of these guys, every group saw a gain in mass of the distilled water. And again, my hypothesis is what I just talked about the dialysis tubing on the inside of the bag might have some trace elements there from the processing part, and so therefore had some things dissolved in there from the bag, and therefore why we had water go in there. But we do see a couple groups had very little change in there, and some groups had more. All right, so that's what we would expect. And so then we see each of these gained mass, and this is the correct result, that this should have gained less mass than the sucrose here. So you guys overall got pretty good results. Now let's look at why they gained mass. All right, so here for the distilled water, it should theoretically go in and out equally. We had a little bit more for everybody going in than we had out there, and so that could be because of those trace solutes there. Now let's look at these guys here. So gained mass, can somebody tell me why both of these gained mass and why this one gained more mass than this one? Why does it make sense that sucrose gained more mass than sodium chloride? Jen? That's right. Sucrose is too big to get through the membrane, and so that's the only explanation for that, because what you have here is you had 10 milliliters of a 1 molar sodium chloride solution and 10 milliliters of a 1 molar sucrose solution. The molarity, what that's telling you is the concentration of the solutes. So therefore, when I made the stock solutions, all right, there's the same number of molecules. So 1 molar solution has 6.02 times 10 to the 23rd molecules of sodium chloride and sucrose. So therefore, the concentrations, there's the same amount of solutes dissolved in a liter of water here. And so the concentrations are the same. The volume is the same. The only thing different is the type of solute. And so in this case here, for more water to go in, you have, if we were to blow that up and kind of look at the pores here, all right, so if this is the pores of the dialysis tubing, sucrose is way too big. So you have the same amount of sucrose dissolved as you have the sodium chloride here, but sucrose is way too big to get through the membrane. And so therefore, when you have just pure water on the outside, you're going to have more water go in, all right, and no sucrose coming out. So therefore, the sucrose concentration, that sucrose is going to stay there, and the water is going to diffuse in, versus what's happening do the same thing for the sodium chloride. So sodium chloride, when it dissolves in water, what does it do? Jacob?
It like breaks apart into ions.
Yeah, it breaks apart into ions, so Na plus and Cl minus. So we have that going on, plus our water in there. And so now these sodium chloride ions, these guys are small enough to get through the membrane, and water then also is small enough to get in. So you have the sodium chloride ions leaving and water going in. And so, so therefore, when the sodium chloride ions leave, what's happening to the concentration of the sodium chloride in here? It's decreasing, right? As sodium chloride ions leave, so NaCl, this is going out. Water is going in, you have water going in there. And as water goes in, that's also going to decrease the concentration of sodium chloride. And so you have two things diffusing, in this case, opposite directions here. And therefore, the sodium chloride ions, as they leave, will increase in concentration on the outside. Could this ever reach equilibrium? Yeah, this could reach equilibrium where the sodium chloride and the water keep diffusing until you have equal concentrations of each. All right. Could this reach equilibrium? No, sucrose is stuck inside. So in this case here, nothing's coming out of the bag and distilled water is going in. I shouldn't say nothing is coming out. You do have some random water coming out, but you have more water coming in than you do out. And so therefore, you have a greater concentration of water going in because the sucrose is not moving. And so therefore we have the same, the higher gain in mass there. All right, so that's what you should have seen. So I wanted to make sure and go over this as a class with you so that you could see what you would expect, just in case your numbers didn't show exactly. But most groups, it looks like you guys got pretty good data. All right, any questions on that? We understand that? Okay. All right, let's look at, for a little bit here, the osmosis challenge sheet. Get that out. Go over, I'm going to just talk a little bit about some of the concepts.
What's wrong?
Yeah.
This part 4 that's due Wednesday, you want this on the back of the sheet or on a separate sheet of paper?
On a separate sheet of paper. Alright, so let's look at the osmosis challenge. Let me get a blank sheet here. The first few questions are a more realistic look at diffusion and osmosis with pertaining to the IVs. So the first two questions are about why IVs are not 100% pure water, and what would happen if it was. IVs have salts and things like that in it, so they have solutes. Can somebody explain to me why that makes sense? Jacob?
Because your blood has like salts, and if you were to put like regular water in it, your cells would lose water.
If you put regular water in, would your cells lose water? It would gain water, something like that. Do one of those two things. All right, so let me explain why. I'm gonna draw a little picture here. When you put an IV solution it goes into your bloodstream. Your blood, everybody knows blood is red, but the reason why it's red is because of the red blood cells. So you have red blood cells floating around in your blood, but the outside, what those red blood cells are doing is floating around in a clear liquid called plasma. And plasma, it has that's where the salts and all your solutes are dissolved in your blood. And so you have this liquid that the red blood cells are made. And so the blood, the liquid blood that you've seen when you get cut or something like that, only appears red because of the red blood cells. If we were to remove the red blood cells, the blood would be more clear. Okay, so the plasma. It's only because of the presence of red blood cells. So now, when you get an IV, you're putting, so all of this is in your blood vessels, right? So when you put in an IV, you're putting fluids into your blood. So you're adding fluids to this plasma, this liquid part of your blood. And if that was 100% water that you're adding into this, what does that do to the water concentration in your blood? It's going to increase it, right? And if the water concentration increases in your blood, water will most likely go into your cells. And if it increases the concentration too much, what do you run the risk of happening to your red blood cells? Explosion, right? And that would not be good, all right? So remember that your red blood cells are typically bathed in isotonic solution so that that doesn't happen, so that it shrivel up or explode. And so that's why we don't want to give pure water. So then it's saying here that IV has salts in it instead of being 100% water. The purpose of the salts is so that your concentration is more equal to your red blood cells. Does that make sense? All right, so therefore your blood cells aren't going to shrivel up. Now you don't want to have too many salts in there because then you're going to create a hypertonic situation where water will leave. That's also not good. And so the salts are needed for that. So in order to get that correct concentration of salts in water in the IV, that's what the third question is. What do you need to know? What do you need to know to do that, Scott?
The concentration of their blood plasma, so that you can match it.
Okay, yeah, the concentration of the blood plasma, so you can match it, absolutely. And if it's an isotonic solution, it could also be inside the cells too, so that you have the isotonic situation. Very good. All right, so then, so that's the first three questions. Then it goes through and talks about this experiment that these students did, using dialysis tubing like we did. But instead of, what we did is we used the same concentration but changed the solute. So we had NaCl and sucrose, but we had the 1 molar concentration in each one of these. These guys, what they did is something different. First of all, they had more cells, but they kept the same solute. They used sucrose the whole time and just changed the concentration of the sucrose. So they did something a little bit different here. And so, in looking at this is what their setup is. I'm going to come back and answer this question in just a second after we look at their setup. So they had 10 milliliters of each solution that they made their cells, like you did yesterday. And inside, I didn't write sucrose, but inside there's the different varying concentrations of sucrose, and it tells you also on the outside is distilled water. So if we look at this, it says they masked the bags before and after. And if we look at what we would expect to happen, so let's just look at here. So for distilled water, we should have had that little to no change, right? That the water will diffuse in and out equally, much similar to what we had on the left there in our lab. So we should have little to no change there. Now, all of these bags, B, C, D, E, and F, this is all 100% water on the outside and a 2 molar sucrose solution, 0.2 molar in this case here. So that means that there's 0.2 of a mole, all right, of sucrose dissolved in the water. Where will water move? In, right? Here, in. Now, if we put them all in at the same time and let them sit for 30 minutes, water's going to go in each one of these B through F scenarios. Is it going to go in at an equal rate? No. Which one's going to have gained the most mass at the end of this 30 minutes? Is it B or F? It's one of the extremes. Here B, and I heard 1 as well, or F here. Let's look at what, I'm going to draw another picture here, up here. Here's your bag. So this is your bag. You got sucrose. Sucrose can't get through the pores. So here's your big sucrose molecules. Now, you also have water molecules. Now, when you have water molecules, some of them are free, but what happens when water dissolves sucrose? What does it do to it? Do you guys remember what it does when it dissolves? It surrounds it, right? So you have all these water molecules surrounding whatever your solute is. In this case, it's sucrose. And so on the outside is 100% pure water. There's no solutes whatsoever. So I'm just going to put a whole bunch of dots for pure water. Can you see here that when you have solutes, a lot of your water molecules are taken up by dissolving the solutes, all right? So they're surrounded, they're stuck kind of like little magnets. Remember, they're polar and the charges are attracted to the charges on the sucrose. And so therefore there's less free water molecules that can actually diffuse because the water molecules that are stuck to this can't get through the membrane. So do you see that? Because these guys have no solutes, that these guys are bouncing around, and more of them that are free can bounce into the membrane and diffuse in. There's fewer free water molecules here, so while some of them will bounce and hit the membrane, not all will, and there's few of them to even hit the membrane. And so therefore, you're going to have the more water be able to diffuse into the situation than if you had just one solute. Let's say, let's compare that here. So when you have less solutes, and here's one sugar molecule here, and you have the water molecules surrounding it, but you have, because there's less solutes, you see that you will have more free water molecules that can actually diffuse. And so what's going to happen is you're going to have water diffuse in here, but you can have more water diffuse out because there's more free. Does that make sense to do that? So therefore, the higher concentration of solutes usually will gain the most water because a lot of those water molecules are taken up in the dissolving of the solutes. Does that make sense? Okay.
So when you say the higher concentration of solute, it's like
the less free water molecules to diffuse. And so in this case here, the higher concentration of solutes, you're going to have then more water diffuse in. So if we look at this from here to here, we said that it's increasing, right? But we should have an increasing percent change in mass. And so this one will gain the most, this one will gain some. Okay, does that make sense? Yeah. Okay. So you guys had, I emphasized that. Yeah, all right, some people. All right, so it will get increasingly more. As you go there. All right. Okay. So we're looking at the next one here. Then you have, I gave you the data. So initial and the final mass and the mass difference. And so then you get the percent change in mass. So when it says how to figure out the percent change in mass, final minus initial over initial, multiplied by 100 gives you your percent change in mass. And so in looking at this then, I'll just illustrate one and then we'll just go over the answers here. So, so to figure out this first one, you take final, which is 26.2, minus the initial, which is 26, divided by the initial, and then multiply, which is 26, and multiplied by 100. So when you do that, did you guys get 0.77%? All right. Or if you round it up, 0.8. All right, so then we, by the same token, we do the next one. So 27 minus 26.2 divided by 26.2. And what did you get? I call it some people. Derek, did you do this?
Yeah, I did.
What'd you get?
I got 3.1%.
Yeah, I left it as 3.05, but yes, you're right that it would round up to 3.1. For the next one, so you take 28.1 minus 26.1 divided by 26.1, and you would get what, Grayson?
7.66%.
All right. The next one, you take 29.3 minus 26.4 divided by 26.4 multiplied by 100. And what do you get, Hannah?
10.98%.
Yep. And then the next one, you would get, what, Jacob?
14.82%.
14 point what?
82%.
All right. next one, Tristan, what'd you get?
18.2.
18.2, I get 18.18, but wow, it's 18.2. All right, very good. All right, and so let's just review why we'd want to figure out the percent change in mass. What's the reasoning behind that? Why don't we just do final minus initial and stop at this column here and get the mass difference so we can see whether or not it gained or lost? What's the benefit of doing the percent change in mass? What do you think, Joel?
Because you can't really compare just the final mass because not all didn't all start at the same mass. So you have to do like the relative mass change in order to compare them.
Yeah, absolutely. All right. And then this last one, I'm not going to go over this. This one here, I'm going to have you make sure that you have done. I want to go through and kind of like I modeled this one for you. So this is the same type of scenario, but it changes a couple things. It changes the outside solution to a 0.4 molar solution, and it says use a drawing. When I say please use a drawing there, I'm encouraging you to, if it helps you, a lot of times drawing things out, it helps me kind of work through something if I can't visualize it in my head. And I find that sometimes that students would benefit a lot when I've had in the past students come in for help with questions about this. I find that they're struggling because they're trying to visualize everything in their head and they make silly mistakes because they get concentrations mixed up and so on. And so drawing it out is helpful for, I find, a lot of people. All right, not everybody, but a lot of people. So if that helps you to think through that. This one here, I'm going to grade for right or wrong answers tomorrow. Because tomorrow what you're going to do is we're going to turn in the lab. So I'd asked you to do this last night, so it should be done, but if you think you did it wrong based upon what we did today, you have a chance to fix it. Tomorrow when you come in, I'm going to collect your lab. The three things I'm going to collect with your lab is your hypothesis sheet, so the sheet that you drew and made your hypothesis and did all your calculations on. I'm going to collect the osmosis challenge sheet, and like I said, I'm going to grade that last question, and then I'm also going to collect those 10 questions at the bottom that I told you we're going to redo tomorrow. All right, so those three things due tomorrow. Okay? All right. All right, so what I'm going to have us do next, I'm going to introduce some information that we need to do the next part of the lab. So we have talked about things diffusing from an area of what to what? High to low concentration, right? And so what we're going to do is next look at that there's something a little bit more that plays a role in which way solutes and water will, we're going to focus just on water, which way water will move besides the solute concentration. And that second thing is pressure. So let's look at this scenario here. This scenario here on the board with sucrose. Here, we said that water is going to go in and sucrose can't go out, and so therefore this will never reach equilibrium because you'll never have a concentration of sucrose out here. So water will continue to go in. If we let it set overnight or for days, what do you think would happen? Could be one of two things that could happen. Scott?
It could take up all the water.
All right, it could take up all the water if there's enough space inside of there. So probably if you looked at all the water in there and the space inside, it probably wouldn't take all of it, but you're right, it would go in until that space is filled. All right, could it ever stop going in even though there's still distilled water on the outside? When would it stop? If there's no more space inside. So let's say the water keeps on going in, you have 100% water out here, it's distilled water, it keeps going in, and that cell fills up, and that water puts pressure remember, as that water goes in, it'll fill up and put pressure on the outside of the dialysis tubing. If the dialysis tubing is strong enough, it's going to put pressure back, and therefore it won't explode because of the strength of the dialysis tubing. And so therefore you could get to a point where as water diffuses in, there's enough pressure, not enough room, and the dialysis tubing won't expand anymore. And so even though you have distilled water, still a higher concentration of distilled water on the outside, you're not going to have distilled water go in anymore because there's no more room and that pressure is being exerted on the outside. Does that make sense? All right. The second thing, I said there's one of two things that could happen. The second thing is that the water could go in, and what could happen to the cell? Yeah, the dialysis tubing could break because the pressure of the water could actually break the dialysis tubing. That would be like what kind of cells? The red blood cells, all right? Animal cells do that, all right? When they're put in a hypotonic solution, because this solution would be hypotonic to the inside solution. And so therefore, that would happen to animal cells. Realistically, the dialysis tubing is strong enough where it would resist the pressure, and so it wouldn't explode. That would be like what kind of cells? Plant cells, and the dialysis tubing would be like the cell wall, all right, on the outside there. All right, so we're gonna look at something called water potential. And so water potential is a more realistic look about which way water diffuses, taking into account two things, both the solute and the pressure potential. So we're going to take a few notes, and these notes you're going to write on a piece of paper. So you're going to need a piece of paper. You'll fill in the blanks this time. Okay, so let's write the definition of water potential. Water potential. I like to think of it as the potential for water to move, but its technical definition is a measure of the energy available for water movement. So it measures the ability of water to move. Always from areas of high potential to areas of low potential. And there's a equation that shows you this. So it's a little symbol, kind of looks like a little pitchfork almost. That's the symbol for water potential. All right, so water potential, to figure out the potential for water to move from one area to another, two things go, that's an equal sign, two things go into, take into account with this. What's called the pressure potential, so it's with the sub P there. Then its pressure plays a role. Plus the solute potential. There's a little sub S there. And solute will play a role. one thing, a little star here, pure water, so that would be like distilled, pure water at atmospheric pressure has a water potential of 0. What does that mean? That means that there's no pressure and no solids. Let me explain what that means. So up here on our picture with the distilled water right here. So this water is exposed to the atmosphere. So when we say at atmospheric pressure, the atmosphere above us has pressure that is exerting on everything on the earth. So there's a pressure from the atmosphere. This water in the beaker is exposed to that atmospheric pressure. So since that atmospheric pressure is on everything, we don't count that as pressure as part of our equation. So that's why water exposed to the atmosphere would have 0 pressure. There's no pressure here. And it's 100% pure water. There's nothing dissolved in it, so there's no solutes. So we would say that the pressure and the solutes are 0, so therefore the water potential of pure water exposed to the atmosphere would be 0. So then let's see how solutes changes that. So underneath here, let's talk about the two parts. We're going to talk about the solute first and then pressure. So let's look at the solute potential. That's with the sub S there. So we're going to write some things about solute potential. First thing, little bullet here. What is it? It's the effect that solutes have on a solution's overall water potential. So let's talk about what is that effect that solutes have. So let's go back to this distilled water example up here. So we said that the distilled water theoretically are going to go back and forth at equal rates. And so what would happen if I put in some solutes here? So let's say I dump some salt into this outside solution here. All right. What have I done to the potential for water to diffuse into the cell? Have I increased the likelihood of water diffusing in or decreasing? I decreased it, right, by adding solutes. The more solutes that water has, the lower the water concentration, and therefore the less likely that water is going to diffuse. And so therefore, if we look at this then, if the solute potential is going to decrease the water's potential to move, what kind of number would this be? Look at this, think of this as a math equation. So water potential, the overall potential for water to move. Solute potential always decreases the water potential. If you add solutes, it's going to decrease the potential for that water to move because it's lowering the water concentration. Physically, like really realistically in the mathematical equation, what kind of number does this have to be in order to always decrease this? A negative number. All right, absolutely. So two things here. The solutes always decrease the water potential, and it's going to always be a negative number. So let's add that. All right, the addition of solutes lowers the water potential. Of the solution. So therefore, we said that then in the equation, that is always a negative number. Negative. So remember that pure water, what was the water potential? 0, right? So when we, like, in that example I just used on the board, we had distilled water on the outside, the water potential was 0, but when we added the salt, added the solutes, so any solutes will make the solution have a lower or more negative water potential. Okay, which is what we just talked about. So, relating that to this, the equation here, so this is our equation. So that we're talking about the solute potential here. So if there's any solutes, that number is always going to be negative. All right, so in this spot in this equation, if it's pure water, this is going to be 0 because there's no solutes. And then if there's any solutes whatsoever, it'll be negative. And the more negative this number is, the more solutes dissolved. Okay? And so therefore, it always decreases the potential for water to move. All right, so that's the solute potential. So let's look at the second part of this equation and talk about pressure. So the pressure potential, this is the sub P. So let's do a couple bullets with this as well. This is the effect that pressure has on a solution's overall water potential. Let's talk about this then. Let's go back to this scenario up here. And so this one right here, so let's say we're back to pure water here. So you have pure water. All right. When it's exposed to the atmosphere, there's no pressure on that distilled water. What would happen if I were to take a plunger that fit the beaker like this and I push down on the water? What would that do to the potential for water to go into the cell? Bobby?
If I had to guess, it would decrease it because if you're smushing H2Os together, they don't want to move as much.
If you're what?
Smushing all the H2Os together, which you can't really like decrease in size by much.
What do you mean swishing all the H2O together?
I guess if you're not giving it as much room to move around, it won't move around too much. I don't know.
Oh, okay. I see what you mean. So you're saying you're decreasing the space?
Yeah.
Is that what you
I don't
mean?
think it works like that. I'm just,
Right, but then if you're right, if they're not even if they're not moving around as much, that pressure is going to do what? Force them through the pores, and so putting pressure on that will force that water. Even though you're decreasing the space, the pressure is increasing, and that pressure is going to be hit on the glass beaker as well as on the dialysis tubing and force those molecules in. And so therefore, you're going to have an increase of water going in because of that pressure. So therefore, pressure does what to the water potential? Increases it. So therefore, pressure would be what kind of number? A positive number. All right? So let's look at this. It's right there. Those two things down here. All right. So the addition of pressure increases the water potential of a solution. So because of that, the pressure potential is a positive number. Unless, of course, there's no pressure, in which it would be 0. Okay, so there's no pressure whatsoever. So before I put the plunger in that picture on the left, there's no pressure, and so therefore the pressure would be 0. But if there's any pressure, it's going to be a positive number. So looking at then at this here, this is if there's any pressure whatsoever, it's going to always be a positive number, and therefore increase the potential for water to move. Okay, so I'm going to go through an example of this with you to show how both of these go into figuring out which way water will move. So let's do an example.
This one.
Yeah.
For the, like the overall H2O potential, just like what it equals, could it be a negative number or is it always positive?
It can be a negative number. This can be a negative number, absolutely. So what would make it a negative number is if there's more, if this number is more negative than this number. All right. So like going, you know, if I were to take this and you have the cell and this is distilled water. So the water potential out here, the pressure is 0 because it's open to the atmosphere, the water. But let's say I add in, like I said, add in the salt, NaCl. So it was, the solute potential was 0, but when I add in the salt, it makes it a negative number. So let's say it's -4. And so you add these together, you get a negative overall water potential. Yeah, absolutely. So let's give it an example. I'm going to use with potato cells because that's what we're going to use in our next part of our lab. So let's say this is the beginning of our experiment here. So we're going to put some potato, a chunk of potato made out of potato cells in a solution. All right, the solution is going to be pure water. And here's your potato cell. So when we look at this, when we figure out the water potential of the pure water, we take into account the solutes and the pressure. This is pure water, distilled water exposed to the atmosphere. So what's the solute potential? 0, right? What's the pressure? 0. So therefore, the water potential is 0. Let's look at what the potato cell. Is potato cell pure water? No. All right, so we for sure know that there's going to be some solutes in the potato cell. So I'm just going to give you, let's say the pressure in the potato cell is 0, and then the solute potential, let's say, is -3. So then the overall water potential here is -3, taking into account the solutes and the pressure. So therefore, water will diffuse where? Into or out of the potato cells? Water is going to diffuse into the potato cells. And when thinking about this in this new way, it's diffusing from a higher water potential of 0 to a lower water potential of -3. All right, and it's -3 because this has some solutes in it, so it's not 100% water. So we're going to expect the water to go in. When the water goes into the plant cells, how is it going to affect the pressure? It's going to increase it, right? All right, until, remember, water will go in until the cell wall resists that pressure from the water. So therefore, this plant cell is never going to explode, but the water will stop diffusing in due to the pressure buildup inside and the strength of that cell wall. So let's look at the after. So here's your plant cell after still in distilled water, still in pure water. So that means the outside still has a water potential of 0, right? But let's look at the inside of the potato cell. The inside of the potato cell, let's look at the solute with the pressure plus the solutes. So now we're going to get an increase of pressure because water is going in. So what happens is when the pressure potential, let's say it's a 3, and the solute potential add together to equal 0 in this case, 3 plus negative 3. So remember that this is a positive number, pressure is always positive, solute is always negative. Notice here that this and this, the cell and the solution, have an equal water potential. That means that you're not going to have a net diffusion of water inside anymore. Why? Because as that water diffused in, that pressure built up and there's not enough room, and therefore it's going to resist expansion because of the cell wall. Alright?
Will it always work out that way, or is it just?
It usually, yes, it'll always work out that for plant cells. For animal cells, the water will keep going and they don't explode. Alright, but for plant cells, okay? Alright, this is where we will stop.